In class, I introduced the idea of antiderivatives. So I want to explain a little bit more about how we do that. So I want to remind you, an antiderivative is a function that has a derivative of some function that we are given. So if I ever see this statement, say some function g of x is an antiderivative of a function f of x, that's equivalent to saying that the derivative of g equals f. So sometimes we talk about operator notation. When I take a derivative of a function g, I get a new function f of x. And so I'm going to write this in operator notation, that the antiderivative, it's like taking derivatives backwards, the antiderivative of a function is some function g. So every time I take a derivative, there's an equivalent inverse derivative or antiderivative. So let's look at a few examples. First, I have the derivative of x to the fourth. Well, we know that that's 4x cubed. So just like with inverse functions, there's an equivalent antiderivative statement. And that antiderivative statement says that x to the fourth is an antiderivative of the function 4x cubed. Now, turns out that's not the only one. For example, x to the fourth plus 3 is also an antiderivative of 4x cubed. And the reason is, if I were to take a derivative, the derivative of 3 equals 0, and so I get back 4x cubed. In fact, there's a whole family of these antiderivatives, and so we usually write x to the fourth plus some constant, which we don't say what it is, so we'll say plus c, is the family of all possible antiderivatives of 4x cubed. Okay, so let's take a look at another example. If I had the derivative of sine of 4x, let's see, we know that the derivative of sine is cosine, but there's a chain rule because it's not just an x in there, so the derivative of 4x is 4. So I find that the derivative of sine of 4x is 4 cosine of 4x. And my equivalent antiderivative statement is that, well, there's a whole family, remember. The sine of 4x plus some constant, because there's a whole family, that's the family of all possible antiderivatives of 4 cosine of 4x. The derivative of the logarithm of x squared plus 1, u prime over u, so it's 2x over x squared plus 1. That's the statement about derivatives. The equivalent inverse statement is that the logarithm of x squared plus 1 plus a constant is the family of all possible antiderivatives of 2x over x squared plus 1. Now in this last example, because x squared plus 1 is always positive, I don't need an absolute value, but in general I would want to think about that absolute value as well. Okay, so those are some examples of equivalent statements between derivatives and their antiderivatives. Everything that you know about derivatives has an inverse telling me about antiderivatives. On the previous slide, I pointed out that if you take an antiderivative and you add a constant, you're guaranteed to find another antiderivative because the derivative of the constant is 0. And so now I'm going to ask the opposite question. Is there any other way to get a new antiderivative? So suppose that I have two functions. I have f, big F, and g. I have big G, and I'm going to say that both of them are antiderivatives of the same function. Now they might be the same function plus a constant, but I don't know if that's really true, and I want to see if there's any other possibilities. So if I say, what's the derivative of their difference? Well, the rules of derivatives say the derivative of a difference is the difference of the derivatives. So I'm going to take derivatives of f of x, big F of x, and big G of x, and subtract. Now, because big F is an antiderivative of little f, I know that the derivative of big F is little f. And I know that the derivative of big G is also little f, and so I subtract little f, and they cancel. And so what I find is that the difference of my functions has a derivative that's 0. What kind of functions have derivatives that are 0? Well, as long as f and g are continuous, so that there are no breaks in the functions, this tells me that f minus x must be a constant. So f of x minus g of x is constant. That's the only way you can have a derivative of 0 and be continuous. So that means that f of x minus g of x is some constant, or my function f of x is the same as g of x plus some constant. So it turns out the only way to find two antiderivatives is to find one antiderivative and start adding constants. Well, now that you know a whole family of rules of derivatives, every rule you've learned about derivatives gives me an equivalent statement about antiderivatives. So here I have a whole bunch of some of the rules. We know that the derivative of x to the n is equal to nx to the n minus 1, and so I write down the antiderivative rule. If you ever see nx to the n minus 1, I know its antiderivative is x to the n plus a constant. Let's look at an example. If I saw what's the antiderivative of 5x to the 4th, I know that must be x to the 5th. But we have constants that we don't know about, so there's a whole family, infinitely many answers that all have the same derivative. Now there's one special power that we have to be careful about, and I want to remind you that if I have x to the negative 1, that's 1 over x, that did not come from a power, it came from the logarithm. So every single rule that I have, derivative of the exponential is the exponential, I have an antiderivative rule. The derivative of sine equals cosine, I have an antiderivative rule. The derivative of cosine equals negative sine, I have a corresponding antiderivative rule. And the rules that we learned recently about inverse trigonometric functions also give me antiderivative facts. So it's your job to be able to recognize derivatives going forwards or backwards. Alright, so now let's get to the heart of the problem. We will be given functions, and we have to find their antiderivatives. So, what are some strategies? Every rule of antiderivatives result from recognizing where it came from in a derivative. And so what we're going to do is we're going to look at the formulas, and we're going to guess the answer smartly, and then check. And as we get more familiar with it, we can do some of the steps quickly and automatically without having to sort of think through all the steps. But I want to demonstrate by thinking about the rules of derivatives. So here, the first example, I want to find the antiderivative of x to the fourth plus x squared minus 2. And what I need to do is I need to look at each term and ask myself, where did that come from? What is that the derivative of? So I look at the first term, x to the fourth, and I ask myself, okay, what rule do I know that gives me a derivative of x to the fourth? So I write it down. It had to come from x to the fifth. The derivative of x to the fifth is 5x to the fourth. The only problem is I don't have a 5. So what I'll do is I will put it in. I want to find an antiderivative of 5x to the fourth. But you can't just multiply by 5, you have to multiply by its inverse. So these 1/5 and 5 are inverse, so that when I multiply them, I get back x to the fourth. And now I go back and I say, okay, what else? I have an x squared. Well, what gives me a derivative of x squared? That came from an x cubed term. If I take a derivative of x cubed, I get 3x squared. And again, I don't have the 3, so I'll put it in along with its inverse. So I get plus, oops, let me change the color, plus 1/3 3x squared. Now I have, again, introduced the constant I needed to get a derivative, and the 1/3 so that I didn't change the answer. Finally, I have the 2. Well, where did the 2 come from? I should be able to recognize that minus 2, I know that. If I took a derivative of 2x, I would get that number 2. And so I'm all good to go. So what do I have? I have 1/5 times the derivative of x to the fourth, so the derivative of x to the fifth is going to be 1/5 x to the fifth. And then the second term, I've got 1/3 times the derivative of x cubed, so the second term in the antiderivative is 1/3 x cubed. And the last term was minus 2, so that came from the derivative of subtracting 2x, and there's a whole family of these. Don't forget the plus c. 1/5 x to the fifth plus 1/3 x cubed minus 2x plus c. So when I say guess smartly and check, what I'm referring to is recognizing x to the fourth is part of 5x to the fourth, which is the derivative of x to the fifth. And x squared was part of 3x squared, which was the derivative of x cubed. So I'll just do that term by term when they're added, and I can identify the derivatives. So let's go to the second example. I want the antiderivative of sine of 4x plus e to the 3x. So we ask ourselves, what's going to give me a derivative of sine of 4x? Well, sines and cosines go together, so it must have come from cosine of 4x. Alright, so what is the derivative of cosine? Well, the derivative of cosine is negative sine. So I get negative sine of 4x, and I have a constant multiple, sorry, not constant multiple, I have a chain rule. I need to multiply it by 4. And so the derivative I would have expected to see was negative 4 times the sine of 4x. Now, what's missing? I have sine of 4x. I need the negative 4. So I'm going to multiply. I need to find an antiderivative. I need to multiply by negative 4 sine of 4x because that's an actual derivative. But I need to multiply by the inverse, which is negative 1/4. The second term I need to look at is e to the 3x. Well, what gives me a derivative of e to the 3x? E to the 3x comes from the derivative of e to the 3x itself. I would have gotten e to the 3x times the derivative of 3x, so that's 3 e to the 3x. And notice I'm missing the 3. So I multiply by the inverse and 3. Oops, that's not parentheses, I want the other bracket. So using the guess and check idea, I've identified that the sine of 4x came from the derivative of cosine, and the exponential came from the derivative of the exponential, and I can now write down my antiderivative. The antiderivative is negative 1/4 cosine of 4x plus 1/3 exponential of 3x plus a constant. And again, I found the family of all possible antiderivatives of the original function using this idea of guessing and checking. All right, well, this third example is trickier. And the reason it's trickier is that I have things multiplied. So if I look at this, what do I have? I have 2x squared, and I have cosine of x squared, and I have, on the other term, I have sine of x squared. This first one looks a little trickier. Let's see if I can guess where that sine of x squared came from. We might guess that it came from a cosine, right? The cosine of x squared. So what happens if I take a derivative of cosine of x squared? Let's see, I get negative sine of x squared times a 2x. And so I have the sine of x squared, but a 2x. If I try to multiply and divide by the inverse, it's not a constant. There's this x. So something else is going on. This is weird. I don't get a single term. And so I have to think a little more deeply. Let's think about these together. Hey, notice this. 2x and 2x squared. At some point, we would want to think, well, maybe it came from the derivative of x times the cosine of x squared. Because the product rule would give me two terms. So what would I get? I would get the derivative of x is 1, leave the cosine alone. Now let's leave the x alone and multiply by the derivative of the cosine. I get negative 2x sine of x squared. And what do I get? I get cosine of x squared, and I get negative 2x squared sine of x squared. Hey, that's really close, except that sine and cosine are backwards. So let's change our order. What if I take derivative of x times the sine of x squared? Okay, so the derivative of x first, take the derivative first, leave the second alone. And now we'll leave the x alone times the derivative of sine, so that's going to be cosine of x squared times 2x, so cosine of x squared, and voila, or voila, as we might want to say, voila, we've found the answer. The sine was really coming from the x sine of x squared's first term, and 2x squared cosine of x squared is what's coming from the second term. And so the antiderivative is going to be x sine of x squared. That's one of them. There's a whole family. Okay. Now the moral of this is antiderivatives are trickier than derivatives. You really have to look at it and say, what's possible? And in this example, the product rule was hidden. There's a product rule here. And you just have to be able to recognize it. So we start by learning the basic rules, and then we start with practice, developing better skills. So I just want to quickly summarize some basic tools that you can use. Every antiderivative rule comes from derivative rules. So we know how to take derivatives of sums. You just take the derivatives of the parts. And so if you see a sum in an antiderivative question, you can find the antiderivatives of the individual terms. The derivative of a product is the sum of two pieces. And so the antiderivative rule requires that you have both parts added before you can find the antiderivative as a product. Similarly, the quotient, the only way you're going to get a derivative, an antiderivative that's a quotient, is you would have had to have all the parts of the quotient rule in your formula. So the only one that's really easy to use is the sum rule. Both products and quotients are incredibly tricky. So we usually don't see them very much. We don't know how to deal with things unless they appear in a perfect product form, like that last example on the previous slide. Now, in particular, if I see only one part of a product, there's no rule. Or if I only see one part of a quotient, there's no rule. You can't take the antiderivative of the pieces and expect to get the answer of the product. It doesn't work. Similarly, the chain rule, if I take a derivative of a function that's a formula, so here this u is some function rather than x, the chain rule says you take the derivative of f, big F, so that's little f. I take the derivative, so this is, let me actually write that in, that might help. This is big F prime of u times the derivative of u, which is u prime. Okay, so the antiderivative of f prime of u times u prime will be the original function. So what we're looking for is if we're going to use the chain rule in reverse, we need to see a derivative that we recognize, and we have to have the derivative of what was inside that function. So I have a hint here, or a rule. If there's everything but a constant multiple to get u prime, you can fix it. But if there's a variable missing, there's no fix. So I have an example down below. I'm looking for the antiderivative of x e to the minus x squared. And I recognize that e to the minus x squared, if I took its derivative, so this is the guess and check, I notice that if I took the derivative of e to the minus x squared, I would have gotten negative 2x, that's the derivative of negative x squared, times the exponential of negative x squared. And comparing formulas, x e to the minus x squared is part of my formula. So what do we get? We are finding an antiderivative all that was missing was the negative 2, so I'm going to multiply by inverses, negative a half, negative 2x e to the minus x squared. And I was able to correct it by using a constant. And now I recognize that I have my antiderivative is negative 1/2 e to the negative x squared, because that was the antiderivative of the formula, plus c. On the other hand, if I just had e to the minus x squared, what was missing? I'd be looking for the antiderivative. What was missing was negative 2x, so I would have to do negative 2x e to the minus x squared. And what was missing is 1 over 2x. Now the problem is, this is not a constant. And so this is one of those funky product things. This is a product, not a constant multiple. And so there's no rule to keep going. So we have to stop. There's no rule. Now there might be an answer, but we don't know how to find it. And that's an introduction to antiderivatives. There's a link on Canvas that gives you a web app, lets you practice computing antiderivatives of basic formulas. I encourage you to go and try that out. I'll see you on Monday.